Hey guys, today we're going to be learning about slope fields. Now a slope field is a pictorial representation of all the possible solutions to a differential equation. Remember that a differential equation is the first derivative of a function, which can be denoted as either f prime or dy dx. Thus the solution to a differential equation is the function, which would be f of x or y. Now let's say if you had this particular differential equation. Dy dx is equal to x plus 3. If we go through the steps of solving for the function, we would have to separate the variables, integrate both sides, and we would get y equals half of x squared plus 3x plus c. This is what we know of as the general solution. And this represents all of the quadratic functions that could be the solution f of x. A slope field is going to be the graph of this, the general solution. And then what we could do is sketch the particular solution if we know the initial condition, which is what we're going to go through in a moment. Now in the AP exam, you are expected to do these 4 things with slope fields. 1, you should be able to sketch a slope field when you're given the differential equation. If you are given a slope field, you should be able to draw a particular solution. Both of these 2 things we're going to do in the next example. And then you're also expected to match a slope field to a given differential equation and match the slope field to a solution of a differential equation. So let's practice 1 and 2. We have here the differential equation dy dx is equal to x minus 1. Now when you're given the graph to sketch a slope field, you're going to see all of these little points here representing coordinates. As we know, the coordinate grid, this is 0, 0, and then this is -1, 0, -1, 1, etc. In order to sketch a slope field, what we do is we look at the differential equation that's given, and we're going to plug in appropriate variables. So for this slope field, we have x minus 1. So what I'm going to do is I'm going to plug in x is equal to -2, which represents this vertical line right here. If I plug in x is equal to -2, what I would get is -2 minus 1, which is -3. So when x is -2, the slope, because remember dy dx, the derivative represents the slope, would be -3. So what we do is we put little tick marks to indicate kind of like what the slope would look like. If it's -3, that means that it would go down, and it would be pretty steep, so it would look something like this. So this represents my slope of -3. Doesn't have to be particularly exact, right? Like I don't know exactly if this line has a slope of -3, but it should be close. See, if I were to go down 3 and right 1, I should be able to connect to this little tick mark here. Now if I plug in -1, which is this vertical line, I would get -1 minus 1, which is -2. That means that the slope is not as steep as this one. So when I draw my slope, it would be more like that. If I plug in 0, I get 0 minus 1, which is -1. So my slope would have to be -1. Again, not as steep as this one here, which was -2. So it would be something more like this. If I plug in 1, which is this vertical line, 1 minus 1 is 0. And a slope of 0 is a horizontal line. Finally, if I plug in 2, 2 minus 1 is 1. So I would, my slope now is positive, so it would look something like this. So this is my slope field. Now it says here to finally sketch the solution curve through the point -1, 1. So this right here, as you can see, if I were to actually integrate this function, what it would give me is a quadratic. Because if I multiply dx to both sides and then integrate, I would get x squared over 2 minus x plus c. So my parabola could be over here, it could be over here, it could be over here, depending on what the c is. So if you're given the initial condition, what we do is we put the point there at negative 1, 1, which is right over here. And then I would draw the solution curve that goes through these slopes. So it doesn't have to be, again, exact, but it would look something like this. So you follow the tick marks that you've made, making sure that you're going through the initial condition. So that is being able to draw a slope field and being able to draw in the particular solution. Let's try another slope field. We have here dy dx is equal to x minus y. Now here my derivative includes both x and y. So that means that we have to plug in every combination. We would have to plug in, let's say, for example, negative 2, 0, negative 2, negative 1, negative 2, negative 2, negative 2, 1, etc. Okay? Now, this seems like a lot more work than it is. But as you do a few of them, you're going to notice patterns. And then you'll be able to follow those patterns as you work. So let's try a couple. Let's start with negative 2, 3, our very top point. So if I plug in negative 2, 3, what I would get is negative 2 minus 3, which is equal to negative 5. So that means it's going to be a very, very steep slope. So I would draw it maybe something like this. Now if I plug in negative 2, 2, which is the point right underneath, we would get negative 2 minus 2, which is negative 4. So again, it's not going to be as steep as this negative 5. So maybe a little something more like that. Kind of looks the same, but you get the picture. Now if I plug in negative 2, 1, we get negative 2 minus 1, which is equal to negative 3. So again, not as steep, but just about. Pretty steep. If I plug in negative 2, 0, we would get negative 2 minus 0, which is equal to negative 2. So not as steep. So as you can see here with this pattern is that each of these slopes is going down by 1. Negative 5, negative 4, negative 3, negative 2. Now it's going to be negative 1, and then it would be 0. Let's try now going on to the next column. Let's start with negative 1, 3. If I plug in negative 1, 3, I would get negative 1 minus 3, which is equal to negative 4. So it's not as steep as this one, it's actually one more. And I mean, think about the relationship of your numbers. We have increased the x value, so that means by 1, so that means that my slope is going to increase by 1 as you move to the right. So this is negative 4. That means that this will be negative 3, negative 2, negative 1, 0, and 1. And this should start making sense. And even if you don't recognize these patterns, you can just go through this process of plugging in the x and the y values and getting those coordinates. So let's just continue for a little bit just to make sure that we establish this pattern. Let's plug in negative 1, 2. That would give me negative 1 minus 2, which is equal to negative 3. So not as steep as the one above, so maybe around like that. Then if I plug in negative 1, 1, I would get negative 1 minus 1, which is negative 2. And then this one would be negative 1, then this would be 0, and this would be 1. And if you want to verify this last one here, I mean, you can plug in negative 1, negative 2, and we would get negative 1 minus negative 2, so plus 2, which equals to 1. So that means that's your pattern here. So this slope here was negative 5. This slope here is negative 4. That means that this slope would be negative 3, this one would be negative 2, and this one would be negative 1. Let me fix this one. This looks more like negative 1. Now, if you notice, right, I mean, again, you can establish all the patterns you'd like. Look here how we have this 0, and then this 0. So that means, and it's going diagonally. So that means that this will have a slope of 0, this will have a slope of 0, and this will have a slope of 0. And that's kind of the pattern here as well. You can see that this slope here was -4, that's this point here. And then this one at -1, 3, it's also -4. If you look here at -2, 0, our slope was -2. And at -1, 1, our slope was also -2. So it's the slopes here are the same as you go diagonally. So that's another pattern that you could establish. And then these here will all be 1. That means that this one is probably 2. And you can check, right? If I plug in -2, -2. I'm sorry, -2, 0, -2. If you do 0 minus -2, you would get 0 plus 2, which is 2. That means that this would be 3, and this one here would be 4. And this would be my slope field. So if the patterns is too confusing, that's okay. Just plug in your numbers. Now I'm giving you graphs that are maybe, pretty big in the sense of you'd have to plug in a lot. Sometimes you don't have to plug in that much, or sometimes the patterns are more evident. Now we'll come back to sketching more slope fields, but let's see what the other expectations that you'll have, which is to be able to identify a slope field to its differential equation. Now, remember that a differential equation, the slope field rather, is the solution to the differential equation. So what you can do is you get your differential equation and we would solve it. And we only need to solve for the general solution since we don't have here any particular solution. So here I have dy dx is equal to 2x plus 4. I would have to multiply dx to the other side, so that way I have my variables separated. So dy is equal to 2x plus 4 dx. Then you would integrate both sides, which would give me y equals 2x squared over 2, which is x squared, plus 4x plus c. Now this is a quadratic. That means that my my slope field here should look like a quadratic, which is a. Now dy dx here is 2 cosine x. I would have to multiply dx to the other side, so dy is equal to 2 cosine x dx, and then integrate, and we get y is equal to 2 sine x plus c. Now the thing with these is that you'll need to know what the graphs of these functions look like. We would need to know what sine of x looks like. Sine of x is a wave. And for sine, the wave starts, sorry, that looks really bad. I put the line in the wrong spot. Let's try that again. If you have your coordinate grid, sine starts here at 0, 0, and then it goes up like that and goes in the same direction. So it starts with an x-intercept. So when I look here, I have, I've already done A. The one that looks closest to a wave would be C. And if you notice that at the x is equal to 0, it has a y-intercept and then the wave. And I point this out because cosine of x looks basically identical, but instead of starting with an x-intercept, it starts with a maximum or a minimum. So it's also a wave, but it starts at the extrema versus sine that starts at the x-intercept. So 2 would be C. Moving on to the next one here, we have dy dx is equal to x to the third minus 3x. Again, multiply the dx to the other side. We get dy is equal to x to the third minus 3x dx. Integrate, and we get y equals 1 over 4 x to the fourth minus 3 over 2x squared plus c. This is a quartic function. Now, the one thing that you'll need to remember about polynomial functions is that the number of turning points, which is maximums and minimums, is one less than the exponent. Or the exponent also tells you how many x-intercepts you would have. Since this is a quartic function, that means that it would have 3 turning points. So it could either look like this, see 1, 2, 3 turning points, or like this. Again, 1, 2, 3 turning points, having up to 4 x-intercepts. So when I look at my graphs here, the only one that would match would be D. For the last one, it's obviously going to be B, but just so that we can see, right, multiply dx to the other side, we get dy is equal to e to the x raised to the dx, to the dx times dx, Jesus. Integrate both sides, we get y is equal to e to the x plus c. E to the x, that is an exponential function, so typically it looks like this, where it is increasing. So that would be B. So again, we need to know what these graphs look like. Now, you don't need to know exactly what it looks like, but you need to have a general idea. You could have also figured out which are your slope fields, not necessarily by working this out by hand. Like if you look here, this is a linear function. So that means that when you integrate, we're adding an exponent, so it would be a quadratic. This is cosine. When you integrate, you would get sine, so c. When you integrate this was originally a cubic function, so that means that my solution would be a quartic function. So you can pick up on these tricks. However, if you do not feel confident in that, then you can just integrate, find the solution, and figure out which graph matches. Now here we are going to identify which of these slope fields matches the solution. So this is a little bit simpler because you don't actually have to do anything. You just look at the equation and see which of these slope fields makes sense. So first we have y equals x to the third. That is a cubic function. So you should know that cubic functions look like this. If I look here at all of my options, the only one that kind of has that S shape would be this one here. So it would be F. For number 2, we have y equals the square root of x. The square root of x, remember, is limited to positive values. It can never be negative because we cannot have a negative inside of the square root. And if you look here, the only graph that does not have anything on the left side of the y-axis, so for negative x's, would be B. For y equals 1 over x squared, this is a rational function. That means that at x is equal to 0, the denominator, we have a vertical asymptote. Vertical asymptotes on slope fields are denoted as either blanks, like there is nothing at that particular x, or you may see a vertical line to indicate that even though there's no function there, vertical lines mean that it's undefined. So I look here and I look at where my x is equal to 0, and I see in D that there's no tick marks. So that must mean that this is the vertical asymptote. So this would be D. Now remember what I said about the graph of cosine. The graph of cosine is the same as the graph of sine, but for the at the y-axis, at x is equal to 0, it starts with a maximum. So it's going to be a wave that starts with a maximum at the y-axis. So when I look here at my graphs, the only ones that has that is E. See how this looks like a wave, and then at the y-axis, we have these maximums. So this would be E. For y is equal to tangent of x. Tangent of x looks almost like cubic functions with vertical asymptotes, and then it just repeats in that fashion forever and ever. So the only graph that looks like that would be C. And finally, y is equal to x. That is a linear function that is increasing, and the one that looks like that would be A. So that's basically everything that you're expected to be able to do on the AP exam. Sketch a slope field, sketch the particular solution, identify a slope field from the differential equation, and identify the slope field from the solution. Now let's look at a sample multiple choice question. Shown below is a slope field for which of the following differential equations? Now what we can do here is we look at the slope field. I do not expect you to start plugging in x and y's for each and every single one of these to make sure that it matches. However, what we can do is pick an easily identifiable slope, such as here along this x is equal to -1, we see that the slope is all 0. We can pick corresponding coordinates and plug them in to make sure that that differential equation is equal to a slope of 0. So for example, let's say if I were to plug in -1, let's do 1, because if I do -1, 0, it's clearly going to give me 0. But if I do -1, 1, and I multiply them here, what I get is -1, which does not equal to 0. So since my slope here is 0, so this is not it. Now if I plug in -1, 1 here, I would get -1 times 1, which is -1, minus the y, which is 1. And that gives me -2, which also does not equal to 0. So it's not B. Now let's say if I plug in -1, 1 into this differential equation. We get -1 times 1, which is -1, plus the y value, which is 1, and we do get a slope of 0. So far, that seems to work. But let's test this one just to make sure, and if anything, we'll come back to see. Because sometimes, right, with the multiple choice, the same coordinate can work for two differential equations, but it may not necessarily work for a different coordinate. So since this works, that's great, but we may come back to it if this also is equal to 0. So now let's plug in -1, 1 into this equation. -1 times 1 is -1, plus the x value, which is -1, and that gives me -2, which does not equal to 0. So we lucked out that we picked a coordinate that worked only for C. So C would be the answer. Now this is a sample FRQ that involves slope fields. Consider the differential equation dy dx is equal to x over y. On the axis provided, sketch a slope field for the equation. So that's what we're going to start off by doing. So that means that now we have to plug in all of the coordinates here. Now if you notice that for the y, if y is equal to 0, because it's in the denominator, which is this line here, the x-axis, my slope will be undefined. So I'm going to leave this line here blank because it's undefined. But we can plug in all of the other coordinates. So let's say if I start off by plugging in -2, 1. Then it would be -2 divided by 1, which is -2. If I plug in -2, 2. -2 divided by 2 is -1, so slightly steeper. And if I plug in -2, 3, we get -2 over 3, which is a fraction, so it's going to be steeper than -1, so something like that. Now let's plug in -1, 1. -1 divided by 1 is -1. If I plug in -1, 2, we would get -1 over 2, which is -1/2, so steeper. And if I plug in -1, 3, we get -1/3, which is also steeper. So notice that if we get these here, the slopes above would be steeper. Let's say if I plug in, what is this, 0, 1, then it would be 0 over 1, and anything divided by 0 is 0. So this is going to be 0. Since all of these x values here are 0, that means that all of these slopes would be 0, because 0 divided by anything would be 0. So that takes care of those. Now we're going to come on this side. If I plug in 1, 1, 1 divided by 1 is 1. If I plug in 1, 2, then it would be a fraction, so it would be steeper. And if I plug in 1, 3, it would be 1/3, so also steeper. So as we go up, the slopes get steeper. So that's one thing to keep in mind. So if I plug in 2, 1, my slope would be 2, so steep. Then 2, 2, it would be 1. 2, 3 would be 2/3. Come down to the bottom here. If I plug in -1, -1, -1 divided by -1 would be 1. Then if I plug in, again, it doesn't matter the order in which you start plugging in. Notice I'm kind of just going around and making sure that all of these tick marks are taken care of. If I plug in -2, 1, the slope would be -2. Sorry, -2, -1, the slope will be +2. If I plug in -1, -2, it would be steeper than this because it would be 1/2. So it's getting steeper as I go, it's getting less steep as I go down. So that's something that you can keep in mind. Again, because these do not have to be exact, they just have to have a general slope for the general behavior of this graph. Now, if I plug in 1, -1, I would get -1. If I plug in 1, -2, I would get -1/2. And if I plug in 1, -3, it would be -1/3. Finally, over here, if I plug in 2, -1, I would get -2. 2, -2 would be -1. And then 2, -3 would be -2/3. So this is my slope field. So that takes care of part A. For part B, it says to sketch a solution curve that passes through the point of 0, 1 in your slope field. So we're going to go to 0, -1, which is here. A particular solution that goes through this, well, that means that we got to follow these tick marks, and you can see that this kind of forms like a parabola. It doesn't have to go through all of your tick marks. It just has to follow the general behavior. So that would be my graph for the particular solution. Now for C, it says to find the particular solution to the differential equation with the initial condition f of 0 is equal to -1. So here we're going to have to solve. So we have dy dx is equal to x over y. Now what I notice here is that my y's are diagonally across and so are my x's, so we can cross multiply. And we would get y dy is equal to x dx. Now we integrate. This would give me 1 over 2 y squared is equal to 1 over 2 x squared plus c. Initially, when I solve my differential equation, before trying to solve for for y, I'm going to solve for c first. So we're going to plug in this initial condition. So when x is 0, y is -1. So we would plug that in. 1/2 times -1 squared is equal to 1/2 times 0 squared plus c. -1 squared is +1 times 1/2, so 1/2 is equal to, this is 0 plus c, so c. So c is equal to 1/2. So now we're going to come back here to my general solution, and plug in c so that we can solve for y. So 1/2 y squared is equal to 1/2 x squared plus 1/2. To solve for y, first we would multiply everything by 2, and we would get that y squared is equal to x squared plus 1, and then square root. Remember that when you square root, your answer is always plus or minus the square root of x squared plus 1. But a particular solution is exactly just one solution, and that's when I look at my initial condition. Since my y value is negative, that means that my y must be negative. So my actual answer would be y equals the negative square root of x squared plus 1. And that's slope fields and differential equations.